Ulla's been doing a PhD in Sweden, and cluster shading is part of it. Not all of it, is it? Part of it.
Yeah, that's the most recent part of it.
And very recently, his research that he's done on cluster shading has been presented. He presented it at SIGGRAPH this year. So we're all very lucky to have him here to give a talk on this form of shading.
So yeah, I printed you see the tag at the bottom, analysis in real-time rendering course at SIGGRAPH, which is very popular.
Just speak up a little bit more, just to get over the nose of it.
Yeah. And I guess, yeah, I'm doing my PhD in computer graphics group at the Chalmers University of Technology, and that'll be finished in February, so this will be the last talk for my doctorate.
Hey Phil, do you just want to get that over there in the lights?
Anyway, so I had made a touched up slide deck for this particular occasion, but the USB memory broke and I didn't bring backup copies or email myself, as I usually do. So I'm just going to do the SIGGRAPH slides and try to remember which ones I didn't want to keep. So it was mostly the same anyway, but I didn't say SIGGRAPH everywhere. Clustered shading was first introduced in a paper by myself and co-authors in my group, presented at the High Performance Graphics Conference last year. And if everyone who's not familiar with tile shading, is that a better way? Not familiar with that? All right. Well, I'll cover that anyway and see how fast I should go. So it's an extension on tile shading, and I'll just say, so when I talk about lights, as I will do in this talk, I mean lights that have a finite range. So this is perhaps the most common form of light, except for the daytime light in computer games. You assume that photons run out of steam after a certain range and fall to the ground, and it's pretty reasonable approximation for if you do diffuse lighting. It's not quite as reasonable for specular reflections, specular light. But it helps because it allows you to control the light density in the scene, so you can make sure that not too many lights affect a given part, which gives you unpredictable shading performance. So cluster shading is an algorithm that will allow you to do thousands, or in fact many thousands of lights in real time. So the number of lights is not really a concern anymore. We don't talk about shadows yet. That would be my next talk. No, doctoral. I did have a few slides. It's a paper I've actually just submitted last week, but I have put some slides in that there. So I might do some whiteboard if I have time at the end. Yeah, and everything is dynamic. So there's no pre-computation in this algorithm. It's all done online. And we get out of this what I call robust performance, which is it has low view dependence. So it doesn't depend very much on where the camera is looking, or it doesn't have very many nasty cases like that. And it's pretty quick. And to make my supervisor happy, it can scale up to 1 million lights. But the interesting question when you have lots and lots of light is how many pixels they cover collectively in the end. So not how many they actually are. He likes that phrase. Right. So the problem that I call it clustered shading, and at least one reviewer did have issues with the title of the paper, and I sort of didn't want to hear about that then, but they did have a point. So the problem I'm actually solving is what I call light assignment, where you find which lights are needed for what geometry. So this can be quite a complex problem, and especially solved on a per object basis, where you have thousands of objects and you have many thousands of lights, and that's really where deferred shading traditionally came and solved that problem by doing it in screen space and per pixel instead. However, no one really uses deferred shading anymore because it has a very strong bandwidth limitation. And there are still people that use forms of what you call it, deferred lighting, where you just split the lighting equation into two stages and do some parts first. But I think that's all going now. Pretty much everyone I spoke to at SIGGRAPH does use some form of tiled approach at the moment. And so tile shading just does it on a per pixel tile basis, the light assignment, and cluster shading essentially takes us into 3D and does it on a 3D tile. And that's sort of basically everything. I was going to go over it in more detail now. That's all one. And I will use this as the example scene. It's a cryptic sponsor, and the colorful spheres there are the light boundaries I talked about before. And I put a tree in to make it more interesting. And that's the view we'll be using. The camera, the yellow camera is the view we'll be using for the example. And looking down through the tree and through all the lights. Like this. So there you can see the, well, you can't really see the lion head in the background. So tile shading, you can do deferred or forward. It doesn't really matter so much because the basic algorithm is the same. And it's quite simple because it's a 2D solution, so, and it can be very fast when you have the scene to match it, so to speak, because it is 2D. And this is also what AMD likes to call forward plus for some reason, that they can best explain themselves. And it works like this. So you just divide the screen into tiles, and for example, 32 by 32 pixels. And when we're done, each tile will contain a list of lights that you use for the pixels inside it. So this means that we need to find all the lights that might possibly affect any of the pixels within each tile, right? That's what we need to solve. And a fairly straightforward way to do that is just to do it in screen space, where you find here I've highlighted the bounding box of the green light in screen space. And then you just add the light to those tiles, and then you do that for the orange light, so on. What was the so on slide there somewhere, but anyway. And then you do a shading pass at the end, where you just run a shader for each pixel and loop over the lights and accumulate the shading.
These slides are available online.
Yes.
So Chris, you don't have to take a photo of each one. These are online, these slides.
Okay.
Several copies.
Please place the link in the folder.
Sorry?
Oh, please place the slide folder, link at the folder. And online folder slides.
Yeah.
Thanks. Thanks, Eric.
And by the way, so if anything is unclear, just interrupt me. I mean, this is why we're in a small room works. Right. So this is the view of the actual tile geometry that I pulled out of my demo, or possibly out of our implementation anyway. And when you zoom out to the overhead camera, you see the way they mold the tree, but then extrude all the way back to the geometry in the background. And I think we're starting to see what the problem with tile shading is. So as you can see, the tiles they extend to intersect all the lights in the scene. And the basic problem is that the tiles are 2D, games are typically in 3D. So if you do have a game that's mostly in 2D, tile shading is probably what you want, but in other cases it's probably not.
So each of the spheres there is a light?
Yeah, they represent the radius of the light. And oops, now I what's this guy? Getting bright again. Oh, I'll continue. So here I've highlighted one of the tiles and zoom that up a bit. And as you can see, that tile contains a little bit of the tree, and the lion's share of the pixels are in the background. That's a good hand. Have to do that. Sit down and see her. It was in the slides. No, it's actually not in the notes. And so that means that this single tile looked from the overhead view in six lights, whereas in fact in the background there's 2 lights affecting the lion head. No lights are all affecting the tree, but we still have to use all 6 lights. This is, this is not just a problem of the efficiency here, but it is also a problem of load balancing. So if you have lots of lights, you can get fairly easily situations. I have a colleague who's done research on using tile shading on mobile platforms, and he ended up with these situations where, and it actually happened in practice, so this is something I've said in the past, but now I can have some data to back it up, that just a few tiles with lots of lights in, because they end up in discontinuities, dominate the running time of the whole shading. So it's not just in theory. And he actually ended up switching to cluster shading for the mobile solution as well. Now I've said all that without showing you the slides. Blah, blah, blah. Right, so that's the summary of tile shading. I think I said all of this several times. So we're going into cluster shading. And the key idea is very simple. You just subdivide in the 3rd dimension as well. In the paper we also do normals. So we do subdividing in a higher dimension, you might think of it as. But we do also cluster the view samples on their normals, so you can cull whole back-facing lines. That idea I can summarize by just saying it didn't really pay off very well. So this, as far as I can tell, not really worth the investment. And the reason is that usually your shader will start with the dot product and to check the back-facingness to the light. So you'll just save yourself the tile size times the number of dot products and some overhead for launching the job. So it doesn't really save a lot of work in a well-constructed shader anyway. And it adds overheads to the clustering and so on. Right, so that was the tiles, and if I switch to clusters, and these are the view space and bounding boxes. So we can see that it's along the wall in the back there, it matches the tiles pretty well. Sort of based on the same tile size in screen space, and then subdivided there. Whereas if you look on the tree, there's a lot more happening there. As you can see, they are approximating the actual geometry in the scene a lot better. Looking at it again, tiles, clusters, tiles, bad, clusters, good. And so, if we look at what happens in our example, again, with the lion head and the branch, you see the clusters look like this, and from the overhead view, you cannot really see the volume anymore, but there are a few on the branches there, a few clusters. And there, no lights needed, as we would like, and over here, 2 lights intersecting. A few of them probably only intersect 1 light. And I guess one question about this is, now we get different counts of lights within the same SIMD lanes or whatever when we're doing a shading in a SIMD. And my co-presenter at SIGGRAPH had a good slide for that, because what happens is that you get often similar, if you have constructed your scene with similar density of light everywhere, you get similar length on the light lists, so you end up with a little bit of data gathering, but the lists are fairly minimal storage. It's only, they're shared over quite a lot of pixels still. So anyway, you don't get a whole lot of divergence in computation because you do roughly the same number of iterations in the loop. You just use different lights as input. So it ends up not actually being a problem that we have been able to see. And so here's the algorithm summarized. and I've put forward variety indented. So you first do a G-buffer pass to get at your depth buffer, or a preset pass to get the same thing. Basically, you need to get the sample positions to be able to find out which clusters are actually needed. Although in fact you don't actually have to do that step. That's actually one of the benefits of it. I don't really have any slides that go along with that. I'll probably come back to that later. And then you find out, so you have a whole screen full of samples, you find out which clusters they belong to. That's the first step, cluster assignment. You just compute them. But I'm supposed to tell you that on the next slide. So let's just go to the next slide. So you compute the integer coordinates, basically, into the grid in your view frustum. And so I've got a tuple there, ijk, and inj is just your 2D tile, so that's just your frag chord divided by 32, x and y, and the k is a logarithmic function of the view space depth. And it's not just the log of the view space depth, that's the shape of it, so but it's in the paper, the formula, if you want to use it. And in the demo if you want to just use it. So, finding which unique clusters exist. It's basically a full screen pass, so if you do it deferred, you can do W depth buffer. If you're not doing it deferred, you can do it as a side effect of the fragment shader. And then you can also get transparent stuff in, which is good. And then you just compute this, and in the simplest way, way to implement this, you just set the corresponding cell in the grid to 1. We did a lot more complicated stuff in the paper, because we also did the normal clustering, which means that with the curse of dimensionality, as it's called, the grid, a full grid, would just be too big to store. But with 3D and big cluster sizes, you can just store the full grid. This is very simple. So then you have the ones set to 1 there. Those are the clusters with some geometry in them, and then you just do a prefix sum over the ones, and out comes the index of your. Does that make sense? And again, this can be done in several ways. I do it in a different way in the demo as well. And so light assignment, which is when you actually figure out which lights belong to which clusters. And for the paper, we did really try to push the number of lights. And so we went with a hierarchy of the lights. In the demo that I've got up on my webpage, I have that implementation alongside with the fallback implementation for when Q isn't available, where you just basically rasterize them into the grids, the bounding boxes. So that also works pretty well. In fact, it works better in some cases. Alright, so in the hierarchical case, we just start one thread for each cluster. So in that compact list, and they just traverse the bounding volume hierarchy and discover which light they intersect and add them to the list each. And to be able to do that in a compact list, we just do it in 2 passes. So you count first and then allocate memory in the store. Okay.
So, sorry, can I just go, do you have the entire tree of lights like copied onto the GPU?
Yes, and we build it on the GPU. It's a very simple hierarchy. It's so it's a left balanced full tree, I think you might say. So it's just an array, and you just build it's essentially the same as a vehicle. Basically. But it's a fan out of 32, so it's a high branching factor, and that's just selected to match the symmetry of NVIDIA GPUs. And to a certain degree, a bit word fit as well makes it extra And I mean, with that structure, which is so, what to take the whole thing, we sort all the lights along for the medium point on the Morton mode, space filling curve. You're familiar with this? It's also called the Z curve or the Z curve.
No, I don't know.
No pens. No.
Whiteboard markers down there.
Yeah.
Yeah.
Whiteboard marker. It's a fabulous curve. Use it in everything. And it's got the grid already, so Morton border is just a space filling curve. And I usually start in the wrong direction, so the total limits are bundled, and I probably did this time too. I should go here. And I don't know. Probably back up there. And so on and so forth. So this is the whiteboard marker. It's most no problem. So on. You get the idea. So it's a space filling curve, and you can do it in 3D. And basically, it's also the same as a quad tree. So the coordinates becomes the positions in a quad tree. So it's sort of some equivalence there. So the sorting is in some sense a quad tree construction or whatever format you like. Except that if it's not balanced, it will turn out kind of crap. But we just don't care about that, and just hope that it's kind of balanced. So if, for example, you have more lights on this side and just go in the middle, it doesn't become a space partitioning, it becomes crap. But only somewhat crap, so that's all right. Well, it's working. And it just means you can do a GPU ready sort, which is very that just build a hierarchy. Results. It's fast. Look. I don't know what to say. This is the same scene as before, but with 10,000 lights. So I guess that's a lot of lights. They're pretty small. And you could do lots of interesting light effects without many lights if you wanted to do some global illumination.
As a comparison, like a modern game, how many lights have you seen a scene on a game with the light?
We'll say a couple of thousand.
On a modern game?
Yeah. Well, I mean, from a few years old, I know I have at least one data point, which is Need for Speed the Run. They had at least 2,600 in. Use that figure.
So that's per frame or per level?
That was for the scene, I think. There they wouldn't have more than a few hundred in each view. But of course, there's not 10,000 lights in this view either. They're all through the scene.
So this is potentially 4 times faster, or can't really make that comparison?
It depends.
4 times more.
Yeah. So this is the performance figure for that view, and well, it's not quite twice as fast compared to time for this, and that's a very tough case for time. So. But you can see that the shading time for tiled is much larger than the shading time for clustered, and it's even larger than the light assignment and the shading time, so the efficiency is fairly lot higher for clustered shading. And the other thing to notice is then the 3 ones to the right, there is when we do the normals, and we also do finding the explicit bounds. And neither of those things turned out to be worth it in our case, but there are definitely more smarter ways you can implement those things. And for the latest paper, we have a better way for finding the explicit, approximate explicit bounds. So this is getting a bit too detailed, and we don't understand. Anyway, main thing is, at least for this, is that the normals, when you have normal clustering, doesn't really pay off because the light assignment time becomes a lot larger and the shading time becomes only a little bit smaller. And the main reason for that is that the number of clusters explode. So for 3 by 3, so that's 3 by 3 normals in each cube direction. So that's what, 26, 30, 27, some number. more clusters.
Can I see you're referencing with the 3D subdivision of the scene in depth? Some scenes are very narrow, and some go back, to the distant horizon.
Right.
How does that affect the kind of subdivision?
Yeah, well, since it is, it doesn't actually matter so much as where you put your near and far plane. So it's sort of the ratio between where the near and far plane is that dictates.
Is it kind of almost like a fixed grid that stretches out?
No, it's not. So in our implementation, it's I'm going to go back to the slide. I'm trying to illustrate that with the little box there. So it's designed such that they're as much cubish as possible. This little first part. So they have the same depth, decay there is the same as this height. So
It's a bit
basically-
rid of the view space kind of thing. It changes every time you move the camera.
Sorry, now the grid is fixed in, it changes where it is in world space. It's fixed within the view first.
Yeah.
But so basically what you can think about is you start at the near plane, and then you have your screen space tiling, right? And then take on the near plane the size of that one, and step that far out. That gives you a cube, and then you keep going. And that becomes an exponential function. Depending on your field of view, etc.
So I was thinking like deep into the scene, if the number of cubes from the near to the far plane varies greatly, or whether it's very similar.
Between scenes.
Yeah.
Well, it depends on where you stick your near and your far plane. So, I mean, moving the far plane out, this is the same as with the depth buffer precision. So, if you push out the near plane a little bit, you get a lot fewer clusters. So, EML,
the precision of the light matching, because if you had a deep scene with detail up close but not very far, then maybe you're...
Yeah, so EML, who did the code presentation on Seagraph, he, in the practice, had to solve this problem because they have an open world. He works on Avalanche, and they do these, what's it called, just cause, you might call them. And it's this open world run around that goes kilometers of field of view. So what he did was he simply special treated the first 5 meters, because it's a reasonable thing to do when you're in a game, not writing a paper, just picking up that it works. Mm-hmm. And I would say that this is mostly correlated to the size of your lights. Right, so because you want to have the same number of lights, or you want to have the clusters the size such that you have a good matching between the lights and the scene. So if you have tiny ones which end up on the near plane, they don't really help much because they're all going to contain the same light. So he pushed it out by 5 meters and treated them basically with a tile for the first 5 meters. Squashed them into the first set of tiles, clusters. And then after 500 meters, they don't do lights at all. And in that range he had, I think in his last presentation, 32 depth sizes only. So he went with a fixed, and then he got elongated clusters, not cubical. But he was saying that this actually is causing some trouble. And I have some pretty strong reasons to argue that this is a good... when we did this, I didn't really have a really strong reason, except that it has the sort of same load as your depth. So, you can think of samples have a lower position far away, and you want to have several samples in each box, otherwise it becomes expensive. So it makes sense to have bigger boxes further away, otherwise you'll end up, with single sample clusters if you're looking from far away. So that's all I had, but I have more reason to say this after the shadows. Back to the results, which aren't really the interesting part anyway, so thanks for interrupting. This is another view. There's lots of lights. Look at the tiles. They are bad, I told you. And so there's about 2,000 lights in these things. There's like a lot of colorful blood solid spheres, and I'm happy to report it. For the new paper, I fixed them at their points bright. And this is a heat map showing how much work is going into each tile. So this is for tile, and the white is about 300 lights in each tile. And it looks like this with the last couple. And this is from a scene that's actually modeled by actual game artists. We didn't build this grill to it. We did put all the lights in most of them. All of that craziness. Anyway, I'm sort of out of time, so if I'm going to have time to talk about, can I take a few minutes to talk about shadows?
Yeah,
or how
yeah.
you feel?
Yeah, I think you've probably got 10 minutes. So.
Yeah, so I could probably skip over the transparency fairly quickly, except by noting that tile shading transparency is a problem because you lose them. I mean, if it's going to be good, you have to fit the single layer depth. So it's basically like if you had discontinuity everywhere. If you're looking through, like here is supposed to look like you're looking through a transparent thing in the front there. So you basically lose any information from the depth. If you're unlucky, and that's also view dependent. For clusters, this is not a problem, as long as you come up with a way to discover which clusters are needed, or do the light assignment up front for all of the clusters. And then I had seen, I talked about the year before, Sigurd, where I basically looked at anti-aliasing, how it's affected, and bit transparency. So this is 1,000 lights in the same scene, but with balloons. And this is the deferred variety. It doesn't have to do the bubbles because it can't, so it does the cluster shading here for the comparison is doing 2.2 times the amount of shading work. And despite that, it is, look, so top line is tiled deferred shading, and you can see it scales fairly poorly with increasing anti-aliasing, and then we haven't. I mean, the main reason for wanting to go away from deferred if you're doing multi-sample anti-aliasing is simply memory use. I don't have the numbers on the slides, but 2 million pixels times 16 samples is starting to become a lot of memory plus a lot of bandwidth. Anyway, so it's good. There you go, there's the link.
What API have you developed this on?
We use CUDA and OpenGL combination, or confrontation sometimes. It works pretty well. The only thing I really don't like is that you cannot take a texture from OpenGL into CUDA, like in a black box kind of way. There's something that you have to map it and set it up again in CUDA. That's the main annoying thing that you don't get in complete shaders. Direct 3D, you have the same texture automatically. Other than that, CUDA is better in most ways. And I don't have to worry about shipping it to customers with different hardware. So.
Yeah. Are you doing any work with DirectX these days?
No, I haven't touched DirectX in many years. OpenGL is much more up to date with new features. NVIDIA are really quick pushing out extensions for their hardware when they come up with new stuff. And DirectX is trailing it behind, and I think it's probably hurt as well by Microsoft's insistence on having you upgrade Windows to get new DirectX versions. Whereas I can get the latest OpenGL features on Windows XP. And in brackets I do, not for work, my home computer still runs.
Are you working for, was it Avalanche Studios? Is that?
No, that's my co-presenter.
Oh, okay.
I had deleted that logo from. So, should I improvise on my most recent paper, which I can't give the title of because maybe it will change if we publish. So it's under review right now, and it's about the problem of doing shadows with many lights in this context. And I got to think a bit now where to start this.
We're getting a bit low on time, probably, depending on how much time people have got. Yeah.
Something like that.
Quick hack.
We've got till 2, so it's up to you guys how you want to.
I'll read the big idea. So the basic idea that so the clusters. I mean, you can see if you can get an accompanying slide here somewhere that shows them in action. So yeah, the little blue things. It's pretty hard to see. Let's see. Oh, anyway, I mean there are some kind of approximation of your view-space samples that you're about to shade. So they provide you information of where stuff that needs shading are, but that also means that they provide you information of where stuff that needs shadowing is. So if we have a light, let's see if I do this right, and we're looking here, we see these samples in this cluster. One of the things, if we're doing shadow maps, like cube shadow maps, this gives us some idea of in which direction shadows will need to be cast. And it also tells us roughly how big the cluster is. And we already know how many samples it contains because it's a screen space tile as well, so it's got a fixed footprint. And that tells us what resolution we need on the shadow map, right? Because if we want to avoid aliasing, we want to match the shadow map resolution to the samples on that we're going to see. Pixels. And so that's the basic idea of what I do in the paper.
Does that mean you can only shadow things that are on the screen?
Yes. But you cannot see things that aren't on the screen.
You can see the shadows of things that are not on the screen.
Yes. So these are the things that are receiving shadow.
Oh, okay.
But that's the other thing. It also tells you where. So basically, you'll have a lot of clusters. They'll be in different places. And they'll have different projections on this. This is a cube map, cube shadow map around this point light. And so that tells you if you were to sort of do this reprojection as so this gives you two things. So first you can work out the resolution you need on the shadow map. And the second thing is if you store say a bit for each of these. So you basically do a re-rasterization of the clusters onto the shadow maps. It tells you where the shadow receivers are, which means that you can then you build the same mask for your shadow casting geometry and calc them against it. So you don't actually have to render anything that's not going to cast a visible shadow. So that sort of ties in to what you said. So cube map might look like this. We have a stack of clusters over here. This is their screen, what we can see. So that means that in this case, only this part of the cube map contains. Sorry.
And you can just count.
Right. So this only this cube face has any shadow receivers, which this is all the visible pixels over here.
Sorry, one little question. How's it go with refracted light?
Refracted lighting.
Yes.
Don't think it goes with refracted light.
Just a question.
Yeah. No. So this is just taking the next step from the many lights.
I
Limited
understand,
range.
like as you might understand, refraction of lighting is a big issue, particularly if you want to render something like water and stuff like that.
Yeah, but you typically wouldn't bother with that for your point lights. Maybe for your daytime light, right, your sun, that would be important cue for your daylight. This is for the little point lights, so probably wouldn't bother with reflection for that. I would guess.
Yes.
No, I think
I was just curious.
surely your point lights you can light water as much as you light.
No,
Yeah, alright. In any case, it's not something I've considered for this. So this is more on the efficiency of culling. So you want to find out, so you have some kind of discretization of this cube face, and then you know where the geometry is, so you know that something that would cast shadow and need to be rendered into this cube face can be discarded. And the more interesting thing, though, in my opinion, is that once you worked out the resolution, I mean, if you're looking at something very close and the light is fairly far away, that's going to ask for a very high resolution, right? And But that goes together. This is sort of the situation where all the samples are. Right, this is a full screen, so it's like 1 million pixels. That means you'll need 1 million samples here to cover them. So that's a pretty high-res cube map. But you're not using the other faces. And one thing that's become available recently in hardware is virtual texturing. So you can actually do hardware virtual shadow maps. And they generally work, so for a 2D texture, you have making myself into a corner here. So if this is a 2D texture, you have the physical pages laid out in like 128 by 128 pixels like this. And then you have API to just say, commit physical backing for these ones, but don't bother with the rest. And it doesn't take up any more memory than you've committed physical memory, of course. And so basically that's the ingredients in the paper, and then I look at how to build a system that does this in an efficient manner. And the takeaway, I guess, if I want to present how well things perform, is that the overhead for doing all the management of geometry and doing this bit mass and finding the resolutions is a lot lower than the actual cost for shading in the end. At most like 50% or so.
What kind of counts are you getting on the number of shadows or lights casting a shadow?
Well, the scenes I've used have up to 250 lights casting shadows simultaneously. But the peak frame times are not where the most number of lights are visible. I think I could probably, I haven't really detailed looked at exactly what all the design. I've been busy writing a paper. I didn't think of it. But I guess, so for the worst case timing in the reported figures, there is somewhere around 200 lights and quite a lot of large ones. So like in the worst case, there is around 11 that would have used 8K by 8K times 6 cube maps. But it never goes above 35 milliseconds per frame. So that's on GeForce Titan. Now I probably went over time. Sorry, and sorry about that.
So we'll get a link to the slides and maybe the paper as well. Is it published yet?
No, the paper is under reviews. We're not going to do that.
So we'll get a link up to the paper when it's ready.
Yeah. So not the shadows, but all the other stuff is here. The shadows, this is all not official yet.
Thanks a lot.